Have you ever considered that this moment, the one you are living right now, is not temporary? That it does not simply arrive, glitter for an instant, and then vanish forever into the inaccessible country of the past? What if, instead, this very second is permanent? What if the moment of your birth has not actually gone anywhere? And what if the moment of your last breath is not a distant, unwritten future, but already exists, fixed and waiting, like a distant mountain range hidden in the mist? This is perhaps the most profound and unsettling idea in all of modern physics. It is a concept known as the block universe. It suggests that time does not flow. There is no great cosmic river carrying us from one second to the next. Instead, the entire history and future of the cosmos, every star that will ever shine, every word you will ever speak, every silent thought you have ever had and ever will have, exists together all at once. It is all part of a vast four-dimensional structure, a static block of spacetime. In this strange and beautiful picture, your life is not a story that is being written moment by moment. It is a story that is already complete, finished from the first page to the last, and what we call the present, what we feel as the now, is nothing more than a slice. A single illuminated cross-section of that four-dimensional block lit up by the beam of our own consciousness. But this feels wrong, doesn't it? It feels cold and static and profoundly contrary to every sensation you are having right now. You can feel your own heart beating, a rhythm in time. You can hear the sound of my voice, which flows from one word to the next. Our entire existence is built on the sensation of passage. We experience time as a relentless, forward-moving force. We even feel it change its pace. Think of a moment of pure, unadulterated joy, a perfect summer afternoon with someone you love, a moment that seems to vanish in a whisper. Time flies. Now, think of a moment of intense fear or agonizing boredom. A car swerving towards you on a wet road, a clock on the wall that refuses to move. In those moments, a single second can stretch and dilate, expanding into an eternity. Our minds are not passive clocks. They are active sculptors of time. Neurologists tell us that when we are in danger, our brain's amygdala kicks into a higher gear. It begins absorbing more information, more sensory snapshots of the world, creating denser, richer memories. Later, when our brain plays that event back, it feels as though it lasted much longer. We are, in essence, living in a slightly delayed recording, one that our brain edits for survival. This subjective reality is powerful. It is our reality. So how can the universe be so different? How can this static, frozen block of space-time be the truth, when our own bodies and our own minds scream that time is a rushing, turbulent river? Perhaps you are listening to this in the dead of night, while your city sleeps and the only sound is the rain on the window. Or maybe you are listening on a crowded train, watching the world blur past, a traveler moving through space as you listen to a voice move through time. Each of us is experiencing this now in a completely different context, in a different part of the world, at a different hour of the day. If you feel comfortable, I invite you to share a thought in the comments. Just a few words about where you are in the world and what time it is for you as you listen. It is a strange and lovely thing to think about. All of us connected by these same ideas, yet separated by thousands of miles and countless hours. It helps others on this journey feel a little less alone in the vastness, and it helps this channel be found by other curious minds, drifting in the quiet dark. If you enjoy these voyages, I hope you will like this recording and perhaps subscribe to join us again. It is a small gesture, but it creates a connection, a shared moment in this vast, strange block of time we all seem to inhabit. And now, let us return to the mystery. This idea of a frozen universe did not come from philosophy, or meditation, or a dream. It came from mathematics, specifically from the work of Albert Einstein in the early 1900s. It was Einstein who first showed over a century ago that time is not the absolute universal metronome that everyone, even Isaac Newton, had assumed it to be. He proved that time is deeply, inextricably woven together with space. You cannot have one without the other. He called it spacetime. His revolutionary equations showed that time flows at different rates for different observers. The faster you move through space, the slower you move through time. If you took a long journey on a near light-speed starship and returned, you would be younger than the friends you left behind. This is not a theory. It is a measured engineering fact. The very GPS satellites that guide you home must constantly adjust their clocks to account for this strange temporal stretching. But the most disruptive idea he uncovered was something called the relativity of simultaneity. It is a complex name for a simple, world-shattering idea. There is no such thing as a universal now. You and I, we cannot agree on what is happening at this exact instant everywhere in the universe. If you are on a spaceship traveling at high speed, and I am on Earth, your present moment and my present moment are different. We are, in effect, slicing through that four-dimensional block of spacetime at different angles. And if there is no single true present, if we cannot all agree on what now is, then the only way for the universe to remain logical and self-consistent is if all moments, past, present, and future, are equally valid, equally real. The future is not unformed. The past is not lost. They are simply elsewhere, in other locations in the block of spacetime. This leaves us with the greatest riddle of all. If the future and past are both equally real, why can we remember the past but not the future? Why does time, for us, have a direction? Why does it seem to move only one way, from the cradle to the grave, from birth to death? This is the mystery of the arrow of time. Strangely, almost all the fundamental laws of physics, from gravity to electromagnetism, do not care about the direction of time. They are symmetric. They would work perfectly well in reverse. A planet orbiting a star could just as easily orbit the other way. The equations would be just as happy. But our world is different. Our world is irreversible. We see eggs break, but we never see the shattered pieces leap back together to form a perfect, whole egg. We see ice melt in a warm room, but we never see a puddle of water spontaneously gather itself into an ice cube. We see people age, but never grow young. There is one law, and one law only, that seems to dictate this relentless forward march. It is not a law of motion, but a law of probability. It is the second law of thermodynamics, the law of entropy. Entropy is a beautifully simple and terrifyingly powerful concept. It is, quite simply, a measure of disorder or uselessness. The law states that in a closed system, like our universe, the total amount of disorder or entropy will always increase. The universe itself began in a state of almost perfect, unimaginable order. Think of it as a pristine, new deck of cards, all sorted by suit and number, or a new box of eggs, all perfect and separate in their carton. The Big Bang was not just an explosion, it was the winding of a great cosmic clock. It was an event of incomprehensibly low entropy. Since that first moment, some 13.8 billion years ago, the universe has been moving from order to disorder. The eggs are breaking. The heat is spreading out. The stars are burning their fuel and scattering their atoms across the void. The great structures of the cosmos are slowly, inevitably, dissolving into a uniform, lukewarm soup. This is the arrow of time. It is not that time itself flows. It is that we are part of a system that is collectively moving from an ordered state to a disordered one. Our consciousness, our biology, our very ability to think and remember is built on this process. We remember the past because the past was more ordered. We create memories by taking the chaos of the present and organizing it into neural patterns inside our brain, a process that itself uses energy and releases heat, increasing the total disorder of the universe just a tiny bit. We are surfing on a wave of increasing entropy. The past is simply the direction of low entropy. The future is the direction of high entropy. So, the flow of time, the river we feel rushing us along, may indeed be an illusion, a trick of perception. But the direction of time is terrifyingly real. It is the irreversible unfolding of the cosmos from simplicity into chaos. We are all riding this arrow of entropy, from the singular order of the beginning to the uniform chaos of the end. But what happens in a place where the arrow itself is broken? What happens in a place where time and space become so warped, so extreme, that all of our rules, even the laws of entropy, no longer apply? What happens when a star so massive that it dwarfs our own sun finally dies and collapses under its own impossible weight, tearing a hole in the very fabric of space-time, creating a place where, from the outside, time itself stops? These are the places where the block universe bends, where the geometry becomes a trap, and where the river, if it is a river, flows only in and never out. These are the black holes, and that is where our journey must take us next. So we come to these places in the cosmos, these failures of nature, these regions of absolute victory for gravity, where the very fabric of space-time has given up, torn, and collapsed in on itself. They are not holes. A hole is an absence, an empty space in something. But a black hole is the opposite. It is an almost infinite something crushed into an impossible nothing, a point of singularity. They begin their life in the most spectacular way possible, with a death. Imagine a star, not like our gentle yellow sun, but a true giant. A blue titan, hundreds of times more massive, burning with a fury that lights up its corner of the galaxy. For millions of years, this star is a perfect balancing act. In its core, a nuclear furnace rages, fusing atoms and exploding outwards. This outward pressure is what holds the star up, fighting against the relentless, crushing inward pull of its own immense gravity. But the furnace cannot burn forever. Eventually, the star exhausts its fuel. The fusion sputters. The explosions in the core grow quiet. And in that final, terrible silence, the balance is broken. Gravity, which has been patient for millions of years, wins in an instant. The star's core, heavier than a million Earths, collapses. It falls in on itself at a quarter of the speed of light. In less than a second, a structure the size of a sun is crushed down to the size of a city. The outer layers of the star, now left with nothing to support them, follow, crashing down onto this super-dense core. They rebound in the single most violent event in the universe, a supernova. The star detonates, briefly outshining a billion other suns, scattering the elements of life, the iron in your blood, the carbon in your bones across the cosmos. But the core keeps falling. There is nothing left to stop it. No force in nature is strong enough to halt the collapse. The core crushes itself past the density of an atom, past the density of a nucleus, until it becomes a point, a region of infinite density and zero volume, where our laws of physics, our understanding of space and time, simply end. This is the singularity. And around this impossible point, a boundary forms, a shroud. It is not a surface of matter. You could not stand on it. You could not touch it. It is a boundary of pure, warped geometry. A place in space-time, not a thing. It is called the event horizon. It is the most famous and most misunderstood border in the cosmos. Its definition is simple and elegant and terrifying. It is the precise distance from the singularity where gravity becomes so intense that the speed needed to escape it is faster than the speed of light. Since nothing can travel faster than light, this horizon is a one-way door. It is the ultimate point of no return. Anything that crosses it, a particle, a planet, a ray of light, is trapped forever. This horizon is what makes the paradox of time, the one we discussed, so profound. Let us imagine we are a safe distance away, watching a brave, or perhaps foolish, astronaut drift towards a black hole. We watch them through a telescope. What do we see? As they get closer, they begin to speed up, pulled by the immense gravity. But as they get near the horizon, a strange war begins. The black hole's gravity is now so strong that it is not just pulling on space, it is pulling on time. It is creating a deficit, a deep well in the fabric of time itself. From our safe perspective, their clock begins to tick more slowly than ours. They drift closer to the edge. We see their hand, raised to wave goodbye, but the movement appears to slow down. The light from their spaceship, struggling to climb out of that deep gravitational well, loses energy. It stretches. It shifts from blue to white to red, a deep, fading crimson. They reach the horizon, and there they stop. To us, they will appear to freeze in time forever. A silent, frozen, red-shifted image hovering at the edge of eternity. From our point of view, they will never cross. They will fade over thousands, millions, billions of years as their image stretches into infinity, a permanent, ghostly statue on the shores of space-time. But what do they experience? This is where reality splits. For the astronaut, nothing special happens at all. There is no wall, no sign, no dramatic gateway. They drift past the event horizon as easily as crossing a line drawn on a map. Physics, locally, continues as usual. They are, for a few precious moments, perfectly fine. If the black hole is large enough, a supermassive one like the one at the center of our own galaxy, they might not even notice. If it is a smaller one, however, they would have been dead long before this. They would have been killed by the geometry of gravity. The gravity at their feet, being slightly closer to the singularity, would be 1,000,000 times stronger than the gravity at their head. These tidal forces would stretch them, pulling them apart, atom by atom, into a long, thin stream of elementary particles. This is the poetic and horrifyingly literal term known as spaghettification. But let us imagine a gentle, supermassive black hole. and our astronaut has crossed the line, intact. Now they are inside, and now the true nightmare begins. The rules of the universe have been rewritten. Outside the black hole, the astronaut had 3 dimensions of space: up, down, left, right, forward, back, and 1 dimension of time. They were free to move anywhere in space, but forced to move only forward in time. The instant they crossed the horizon, those roles switched. Inside the event horizon, there is now only 1 direction of space. All spatial paths, no matter which way you turn, no matter how hard you fire your rockets, point to a single destination: the center. And the dimension of time has become the one you can move in. But it is now a time-like path that leads inward. This is the true terror of the black hole. You are not trapped in a place. You are trapped in a moment. The singularity is no longer a place in space. It has become the future in time. It is an inevitable event. It is the end of time itself for you. You can no more avoid the singularity than you can avoid next Tuesday. Firing your rockets to get away from the singularity is now as absurd and as impossible as firing your rockets to try and go back to last week. All paths, all choices, all possible futures now lead to the single crushing point of infinity at the center. The astronaut's journey is over. They, and the information they were made of, are crushed out of existence. Or are they? For decades, this was the story. A black hole was a cosmic prison, a perfect trap. But in the 1970s, Stephen Hawking, while sitting on his bed, had a revelation that changed everything. He was thinking not about gravity, but about quantum mechanics, the physics of the very small. He was thinking about the empty space we talked about, the quantum foam. That foam, as we know, is not empty. It is a bubbling, seething sea of virtual particles, pairs of matter and antimatter that pop into existence, borrowing energy from the void, before crashing into each other and annihilating, paying their debt back in a flash. This happens constantly, everywhere. Hawking asked, what happens if a pair of these virtual particles appears at the exact edge of an event horizon? One particle might fall in, the other might escape. The particle that fell in is lost forever, but the one that escaped, it cannot just exist. It borrowed energy for its creation. It now has a debt it cannot repay because its partner is gone. So, it steals that energy from the only place it can, the black hole itself. This escaping particle flies off into space, looking to us like a faint glow, a wisp of radiation. The black hole, having paid the particle's energy debt, loses a tiny, tiny fraction of its own mass. This process, repeated over and over, is known as Hawking radiation. And it means that black holes are not perfectly black. They glow, albeit with a coldness that is almost absolute. And it means they are not eternal. They evaporate. Over unfathomable timescales, trillions upon trillions of years, long after the last star in the universe has died, these cosmic monsters will slowly, particle by particle, leak their mass back into the cold, empty darkness. They will shrink. And at the very end of time, the last black holes will explode in a final, brilliant burst of radiation, returning everything they ever consumed back to the cosmos. This discovery was beautiful. It was elegant. And it created one of the biggest problems in the history of physics, the black hole information paradox. There is a law in quantum mechanics that is more sacred than any other. Information cannot be destroyed. It can be scrambled, hidden, burned, or shredded. But the information itself, the unique arrangement of atoms that made up a page in a book or a human brain, must, in principle, always be recoverable. But a black hole destroys it. It takes the book, with all its complex information, and crushes it into a singularity. Then it evaporates, returning only a faint, random thermal glow. The information is gone. This was a war between our two greatest theories. Quantum mechanics says information must be saved. General relativity says it must be destroyed. For decades, this was the impasse, until a new, radical idea emerged. What if the information never falls in? What if, as an object falls towards the black hole, all the quantum information that makes it unique, every detail of its existence, gets stuck on the event horizon? What if it is smeared across the two-dimensional surface of that boundary, like a cosmic watermark? This led to an astonishing thought. Physicists calculated the amount of information a black hole could hold, and they found it was not proportional to its three-dimensional volume, as you would expect. It was proportional to the two-dimensional surface area of its event horizon. This is the holographic principle. It is the idea that everything that falls into a black hole, a three-dimensional star, a planet, a person, can have its information fully described on a flat, two-dimensional surface. And if it's true for a black hole, perhaps it is true for the universe itself. Perhaps our vast three-dimensional reality is just a projection, a hologram encoded on a distant two-dimensional boundary. But this, as always in physics, only created a new, more violent paradox: the firewall. If the information stays on the surface, what happens to our poor astronaut? According to Einstein, they should pass through the horizon feeling nothing. But, according to quantum mechanics, if the information is stuck at the surface, the very act of crossing it would create a conflict. Quantum entanglement, the deep connection between particles, would be broken. And this rupture would release an unfathomable amount of energy. The event horizon, that smooth geometric line, would not be a gentle gateway. It would be a wall of pure fire, a firewall instantly incinerating anything that tried to cross. And so, here we stand, at the edge of our own understanding. We are left with a choice. Either Einstein is wrong, and the smooth, beautiful geometry of spacetime breaks at the horizon, or quantum mechanics is wrong, and its most sacred law, that information is forever, is broken by the black hole. We do not know the answer. These dark, silent objects are not just curiosities. They are the battleground. They are the place where our two greatest maps of reality contradict each other, and where they both, perhaps, must fail. They are the silent, patient guardians of the next great revolution in thought, holding the secrets to the true nature of space and time and information itself. And as you rest, as your own local slice of time moves forward, that silent, supermassive black hole at the heart of our galaxy, Sagittarius A, is spinning. It is waiting. It is the dark, heavy heart of our cosmic home. It is strange to think that as my voice reaches you, perhaps in the quiet of 3 a.m, or during a bright, busy afternoon, we are all connected by these same timeless ideas. These thoughts are traveling to you, wherever you are, and it makes you wonder, as you lie there, listening, what time is it for you? Where in the world is your own now unfolding? Black holes are an ending, a point of absolute collapse. They are where the rules of the universe, as we know them, come to a halt, crushed into a single point of infinite silence. They are a full stop. But what if that collapse is not an ending, but a new beginning? What if the singularity at the heart of a black hole is not the end of the road, but a detour? When Albert Einstein's equations of general relativity were first being explored, physicists found more than just collapsing stars. They found solutions that looked strange. They found that in the mathematics, the extreme curvature of spacetime that creates a black hole could, in theory, connect to another region of spacetime. This wasn't just a point of infinite density, it was a passage. The equations showed that a black hole, a point of entry, could be mathematically linked to a white hole, a hypothetical region of spacetime that acts as an exit. A place where matter and energy gush out, but can never be entered from the outside. Together, this in and out formed a theoretical structure known as an Einstein-Rosen bridge. Today, we know it by a simpler, more evocative name, a wormhole. It is, in essence, a tunnel through spacetime, a shortcut. The visual analogy is one you have likely seen, because it is the most perfect way to describe it. Imagine spacetime is not a vast, three-dimensional void, but a simple, flat sheet of paper. You are a tiny hand, and you wish to travel from a dot on one side of the paper to a dot on the other. The journey across the paper is long. It represents a journey of thousands, perhaps millions of light years. But what if you could bend the paper? What if you could fold reality itself, bringing your destination right up next to your starting point? And what if, at that folded point, you could punch a small hole, a tunnel connecting the two? You would not be traveling across space. You would be traveling outside of it. You could step through the tunnel and emerge near a distant star, having completed a journey of 1,000,000 light years in a matter of minutes. This is the glorious promise of the wormhole. It is the dream of instantly crossing the cosmos, of rendering the tyranny of distance obsolete. It is the ultimate shortcut, allowed in principle by the mathematics that governs our reality. And, for a long time, it was assumed that this is how they would work. Then the cold, hard calculations began. Physicists looked closer, and they found a problem. A devastating, fatal flaw. The tunnel is not stable. It is not a bridge. It is a flash. The throat of the wormhole. The tunnel connecting the entry and exit is an object of profound instability. The moment it forms, the universe, hating this unnatural shortcut, this violation of its normal geometry, would cause it to collapse. It would collapse with such speed, such violence, that not even a single photon of light, the fastest thing in existence, could make it through. If you tried to fly your spaceship into one, you would not emerge in another galaxy. You would be crushed in the collapsing throat, which would pinch off into a singularity, just like the black hole you started with. The bridge it turned in was a trap. For decades, wormholes were relegated to the realm of pure science fiction. They were a mathematical curiosity, a road the universe allowed in its blueprints, but had firmly forbidden in its construction. Until, that is, physicists found a theoretical loophole, a way to prop the tunnel open. The problem, as always, is gravity. Gravity is what pulls the throat of the wormhole closed. So, to fight it, you would need anti-gravity. You would need a substance, a form of matter or energy, that pushes instead of pulls. Something that has negative mass, or negative energy density. something that would weigh less than nothing. This sounds like pure fantasy. A magic get-out-of-jail-free card for physics. We call it exotic matter. And you would think this is where the story ends. We do not see negative matter anywhere in the cosmos. Every star, every planet, every speck of dust pulls on every other speck. But the universe, as we have learned, is stranger at the small scales than at the large ones. At the quantum level, in that roiling quantum foam we talked about, the vacuum of space is not empty at all. It is a sea of virtual particles and fleeting energy fields. And in this realm, negative energy is real. There is a measurable, proven phenomenon known as the Casimir effect. Imagine you take two perfect, flat, metal plates and you place them in a perfect vacuum. You move them incredibly close together, just a few atoms apart. Outside the plates, the entire quantum foam is raging. Virtual particles of all wavelengths can pop into existence, bubble, and vanish. But between the plates, the space is so small that only particles of very specific, very short wavelengths can fit. Longer wavelengths, and thus more energy fields, are excluded. This means there is more energy, more quantum pressure, on the outside of the plates than on the inside. And this pressure differential pushes the plates together. That region in the middle, the space with less energy than the empty vacuum around it, is a real, measurable, laboratory-created pocket of negative energy. So, we know this exotic matter can exist. But here's the catch. The Casimir effect produces an amount of negative energy so infinitesimally small it is almost beyond comprehension. To hold a wormhole open, one large enough for a person or a spaceship to pass through, would not require the energy of a few atoms. It would require a quantity of this negative energy field so vast, so dense, it might be equal to the entire mass of the planet Jupiter, or a star, or a galaxy. We would have to find a way to harvest this quantum foam, to refine it, to stabilize it, and to use it to line the throat of a tunnel that is actively trying to crush itself into a singularity. The engineering challenge, then, shifts from the merely difficult to the godlike. But let us be gods for a moment. Let us imagine we have done it. We have gathered the exotic matter. We have built our bridge. We have punched a hole from a point near Earth, call it Mouth A, to a point near a distant star, call it Mouth B. We have a stable, traversable wormhole. We have built our cosmic shortcut. We think we have built a machine for traveling through space. The terrifying, brilliant truth is that we have, by accident, built a machine for traveling through time. Let us explore this. This is, perhaps, the most mind-bending idea in all of relativity. Right now, in the year 2025, we have our wormhole. You step into Mouth A. You step out of Mouth B, a million light years away. You look at your watch. The journey was instantaneous. You turn around, step back through, and you are home on Earth. Both mouths are perfectly synchronized. Both exist in the same now. Now, we take Mouth B. We put it on the back of an enormous spaceship, and we take it for a ride. We accelerate that spaceship to 99.9% of the speed of light. We fly it around the cosmos for, from Earth's perspective, 10 years. Then, in the year 2035, we bring it back and park it right next to Mouth A again. We have done exactly what Einstein predicted. We have taken Mouth B on a high-speed journey. And what happens to clocks that move at high speeds? Time, for them, slows down. For the 10 years that passed on Earth, and for Mouth A which stayed home, perhaps only 1 year has passed for the traveling mouth B. So, in the year 2035, you stand on Earth. You look at 2 tunnels side by side. Mouth A is the Earth mouth. You look through it, and you see a clock. The clock reads 2035. Mouth B is the traveler mouth. You look through it, and you see a clock. The clock reads 2026. You have not just built a bridge. You have created a dislocation in time. What happens now? You can walk into Mouth A, the one marked 2035, and you can walk out of Mouth B into the year 2026. You have just stepped 10 years into your own past. You are a time traveler. And now, all of reality is at risk. Because now, you have introduced the single most dangerous concept in all of logic, the paradox. The most famous, of course, is the grandfather paradox. You walk out of the portal in 2026. You are driven by a strange, terrible impulse. You find your own grandfather, back when he was a young man, before he ever met your grandmother. And you cause an accident. He dies. The logic collapses. If he died, he never met your grandmother. Your mother or father was never born. You were never born. But if you were never born, you could not have grown up, gotten in the wormhole, and traveled back in time. If you never traveled back, you never caused the accident. So your grandfather did live. He met your grandmother. You were born. You did get in the wormhole. And you did go back. And you did kill him. But you didn't. But you did. This is not a puzzle. This is a contradiction. It is a logical 4 = 5. It is the sound of reality breaking. The universe, it seems, cannot allow this to happen. So, how does it protect itself? There are, it seems, 3 possibilities, 3 solutions to the paradox. The first, and perhaps most elegant, is called the Novikov self-consistency principle. This principle states simply that the universe forbids paradoxes. Therefore, any event that would create a paradox is impossible. It means this: you can travel to the past, but you cannot change it. You go back to 2026. You find your grandfather. You raise your weapon, and your hand trembles. You slip on a patch of ice. A bird distracts you at the last second. Your weapon jams. No matter what you do, you will fail to kill him. Or, in a more sinister twist, perhaps your attempts to change the past are the very things that caused it to happen in the first place. Perhaps you go back to save someone from a fire. But as you run into the burning building, you accidentally knock over a lantern, which is what started the fire. You were not changing history. You were fulfilling it. You were always a part of that past. Your free will is an illusion when you are in a time loop. The story is already written, and you are just playing your part. This is the bootstrap paradox, the loop of information. Imagine this. A man in the future finds a tattered copy of Shakespeare's Hamlet. He is a historian. He loves it. He travels back in time using a wormhole to meet the great bard himself in the year 1600. He finds Shakespeare, who is a struggling, not very good actor. He hasn't written any great plays. The historian, in a fit of generosity, gives Shakespeare the tattered book he brought from the future. At least, he thinks, the world will have these plays. Shakespeare, astonished, simply copies the text. He publishes it. It becomes Hamlet. The question, the unanswerable question, is who wrote Hamlet? It wasn't Shakespeare, he copied it. It wasn't the historian, he just found it. The play has no origin. It is an object, a loop of information that wrote itself. It exists in a loop, forever. This is a time loop that does not create a paradox, and so the universe might just allow it. The second solution is less subtle. It was proposed by Stephen Hawking, who found the idea of time travel, and the tourists from the future it would imply, to be an annoyance. He called it the chronology protection conjecture. He suggested that the laws of physics themselves, at a deep quantum level, conspire to prevent time travel. The moment you try to create a stable time machine, the moment you bring the two wormhole mouths into alignment, the universe would fight back. The vacuum of spacetime itself, that quantum foam, would enter a feedback loop. A virtual particle would fly through the wormhole into its own past, and come out before it went in. It would then loop again and again infinitely. This infinite loop of energy, in a fraction of a second, would build into a surge of infinite intensity. The wormhole would be destroyed in a flash of radiation so powerful it would vaporize you, your ship, and your entire experiment. The universe, Hawking argued, protects its own history. It does not allow its causal structure to be violated. The price of building a time machine is instant, total annihilation. But there is a third solution. This one comes from the strange world of quantum mechanics, and it is perhaps the most fantastic of all. It is the many worlds interpretation. This idea suggests that the universe, in order to solve its own paradoxes, clones itself. You travel back to 2026. You walk out of the portal. At that instant, the universe splits in two. You walk up to your grandfather. You succeed. You cause the accident. He dies. And nothing happens to you. You do not fade from existence. You do not vanish, because you have not changed your past. You have just created a new, branching timeline, a new universe. There is now Universe A, the one you came from, where your grandfather lived, and you were born, and you got in a time machine. And then, one day, you simply vanished, never to be seen again. And there is Universe B, the new one, the one where you are standing, a universe where that man died, and your family line will never exist. You are now, in essence, a refugee. You are an orphan of time. You have successfully murdered a man in a universe that is not your own, and you are now stranded forever in a timeline that you broke. This is the frontier. This is what happens when you take Einstein's equations, the ones that govern the gentle curve of starlight and the ticking of a satellite's clock, and you push them. You push them past the breaking point, past the edge of a black hole, and through the throat of a tunnel that should not exist. You are no longer a passenger on the arrow of time. You are no longer just an inhabitant of the block universe. You have found a way to jump the tracks, to edit the pages. The question that remains, then, is, are these just games we play with mathematics? Are they just ghostly stories we tell ourselves, born from the dreams of an equation? Or are we, a species that just learned to walk on its moon, merely a few fundamental discoveries away from becoming the weavers of the fabric itself? The universe is full of things that were impossible until they were not. This entire universe, with its endless black holes and its tantalizing, impossible wormholes, rests on a foundation, a set of ideas. These ideas are so profound, so revolutionary, that they are the very reason we can even conceive of a block universe, or a singularity. Before them, we lived in a different cosmos, a simpler one, a safer one, a prison of comfortable logic. This was the universe of Isaac Newton. For 200 years, Newton's universe reigned supreme. It was a cosmos of perfect order, a clockwork universe. Space was the rigid, unchanging, three-dimensional stage upon which events unfolded. Time was the universal metronome, a great, invisible river flowing at the exact same rate for everyone and everything, from the smallest fly to the most distant star. Gravity was a mysterious force, a spooky action at a distance, a pull that one object, like the sun, exerted instantly across millions of miles of empty space to hold another object, like the earth in its grasp. This universe was predictable. It was mechanical. It was solved. And then, in the late 1800s, a crack began to show. A ghost in the machine. The ghost was light. Scientists at the time, like James Clerk Maxwell, had made a brilliant discovery. They found that electricity and magnetism were two sides of the same coin. And, as a consequence of their equations, they realized that a disturbance in this electromagnetic field would travel outward as a wave that moved at a very specific speed, 186,000 miles per second. It was the speed of light. This was a revelation. Light was an electromagnetic wave. And this led to a very simple, logical question. If light is a wave, what is it waving through? A sound wave needs air. An ocean wave needs water. Every wave we had ever known required a medium to travel through. So, what was the medium for light? They called it the luminiferous ether. The ether, they reasoned, must fill all of space. It must be invisible, massless, and yet perfectly rigid to allow light to travel so quickly. It was the silent, unseen air of the cosmos. And as the Earth orbited the Sun, it must be moving through this ether. We must be experiencing a constant ether wind. It made perfect, logical sense. And in 1887, two American physicists, Albert Michelson and Albert Morley, set out to prove it. They built an ingenious device, an interferometer. It used mirrors and beams of light, designed to detect this ether wind. It was a machine built to measure the absolute motion of the Earth through the rigid, clockwork stage of Newton's space. They turned it on. They took their measurements, and they found nothing. They rotated the machine. They waited for different seasons, for the Earth to be in a different part of its orbit. They tried again. Nothing. No wind, no drag, no ether. This was not just a small failed experiment. This was a catastrophe. It was the most profound, devastating nothing in the history of science. It meant that the speed of light refused to change, no matter which way the Earth was moving. It meant the universe was lying. It meant that Newton's perfect clockwork stage did not exist. Physics was broken. And then, in 1905, a young unknown patent clerk in Bern, Switzerland, published a paper. His name was Albert Einstein. He was not a celebrated professor, but a daydreamer, a man who performed thought experiments. He looked at the catastrophic failure of the Michelson-Morley experiment and did not see a failure. He saw a clue. He proposed a breathtakingly simple and utterly radical solution. He said, "What if the experiment failed because its premise was wrong? What if there is no ether? What if there is no stage to measure against?" And then the revolutionary leap. What if the speed of light is not just fast? What if it is constant? What if it is the one, true, absolute law of the universe? What if everyone, everywhere, no matter how fast they are moving, always measures the speed of light to be the exact same number? This sounds simple. It is the most disruptive idea in human history. Let us run a thought experiment, just as he did. Imagine you are on a train platform. Your friend is on a train moving past you at 50 miles per hour. Your friend throws a baseball in the direction the train is moving at a speed of 20 miles per hour. For your friend on the train, the ball is moving at 20 miles per hour. For you, on the platform, the ball's speed is the train's speed plus the ball's speed, 50 plus 20. It is moving at 70 miles per hour. Simple. This is Newton's universe. Now, let's change one thing. Your friend on the train turns on a flashlight. Light leaves that flashlight at 186,000 miles per second. We'll call this speed c. You, on the platform, measure the speed of that light. By Newton's logic, you should measure the train's speed plus the light speed, 50 miles per hour plus c. But Einstein, taking the Michelson-Morley result as law, said no. You, on the platform, will also measure that light moving at exactly c. Not a single mile per hour faster. This is a paradox. This is impossible. How can your friend on the train and you on the platform both measure the exact same beam of light moving at the exact same speed, c, when the train itself is moving? There is only one way. There is only one sacrifice the universe can make to protect this one unbreakable law. Speed is distance divided by time. If speed must remain constant for everyone, then distance and time themselves must change. Einstein realized that the universe warps to keep light speed constant. To make your measurement of the light beam c come out correctly, the universe must slow down your friend's clock. From your perspective on the platform, their second is longer than your second. This is time dilation. And to make their measurement come out right, the universe must, from your perspective, shrink the train. Its meter is shorter than your meter. This is length contraction. Time and space are not absolute. They are relative. They are a flexible, malleable substance that stretches and shrinks for different observers, all to conspire to protect the one true constant, the speed of light. This was the theory of special relativity. It was not philosophy. It was proven. We measure it every day. Short-lived particles called muons, created in our upper atmosphere, travel at near light speed. Their clocks tick so slowly that they survive the journey down to Earth's surface, a journey that, in Newton's universe, they should not have lived long enough to make. Our GPS systems, as we've noted, must be corrected for it. But Einstein was not finished. He had solved the mystery of light. But his new theory, special relativity, had created a new, enormous hole. It did not include gravity. Worse, it was fundamentally incompatible with Newton's gravity. Newton's gravity, remember, was instantaneous. If the sun were to magically vanish, Newton's equations said the Earth would instantly fly off its orbital path in that very same second. But Einstein had just proven, with special relativity, that nothing can travel faster than light. Not a spaceship, not a baseball, and not information. The information that the sun has vanished cannot travel instantly. It would have to travel at light speed, which means the Earth would blissfully continue to orbit the ghost of the sun for 8 minutes before it suddenly found out and flew away. Newton's gravity had to be wrong. This became Einstein's new obsession. It took him 10 more years. 10 years of struggling with mathematics so complex he was often lost. He was searching for a new picture of gravity. And the clue, the breakthrough, came to him in what he called my happiest thought. He was sitting in his chair at the patent office, and he imagined a man falling from a roof. He realized that as the man falls, he feels nothing. He feels weightless. In his own falling frame of reference, gravity has, for him, vanished. Let's expand this. Imagine you are in an elevator, a sealed box in the blackness of deep space, far from any planet. You are floating. You are weightless. Suddenly, a rocket attached to the bottom of the elevator fires, accelerating you upwards. You are pressed to the floor. If you drop a ball, it falls to the floor, just as it would on Earth. You, in your sealed box, have no idea you are in a rocket. You simply feel a force. You would be perfectly justified in calling it gravity. Now, a new scene. Your friend is in an identical elevator, but it's on the surface of the Earth. The elevator is not moving. Your friend, inside, feels the exact same force pressing their feet to the floor. They drop a ball. It falls just as yours did. This was Einstein's stunning realization. The principle of equivalence. There is no experiment you can perform inside a sealed box to tell the difference between being stationary in a gravitational field, like on Earth, and being accelerated in empty space. The effects are not just similar, they are identical. Einstein concluded they must be the same thing. But how? How can gravity be acceleration? We are not in a rocket. The Earth is not pushing us up. It is just there. We are standing still. This is the leap, the final, brilliant leap. What if, Einstein thought, you are moving? What if you are always moving? In the straightest possible line, but through a curved universe. What if gravity is not a force at all? What if gravity is a shape? He realized that space and time were not a rigid stage. They were a flexible, four-dimensional fabric, a trampoline. And this is what gravity is. It is the curvature of the space-time fabric. The famous summary is perfect. Matter tells space-time how to curve. Curved space-time tells matter how to move. The sun is a massive object. It is a bowling ball placed in the center of the trampoline. It creates a deep dent in the fabric of space-time. The Earth, a smaller ball, is not being pulled by the sun with an invisible rope. The Earth is simply rolling. It is trying to follow the straightest possible path it can, but it is rolling inside the deep, curved dent that the sun has created. An orbit is just a straight line through curved space. And you, right now, feeling the pull of gravity, you are not being pulled. You are simply following your own straight path through the curve that the Earth's mass has made. The only reason you are not falling to the center of the Earth right now is because the floor or your chair is in the way. The weight you feel is not a pull. It is the push of the chair's electrons against your own, the electromagnetic force that is preventing you from following the glorious, weightless, straight-line path that gravity has laid out for you. You are being accelerated, just like the man in the rocket, by the floor. This was the theory of general relativity. It was a staggering, beautiful, mathematical masterpiece. But was it true? Einstein, unlike others, proposed a test. If gravity is just curved space, then everything that travels through that space must follow the curve, even light. He predicted that if you looked at a star whose light passed very close to the sun, you would see the star in the wrong place. The sun's massive gravitational dent would bend the starlight as it passed. There was only one problem. The sun is too bright to see stars next to it. You would have to wait for a total solar eclipse. In 1919, one such eclipse was due. A British astronomer, Sir Arthur Eddington, still technically at war with Germany, led an expedition to the coast of Africa to test the theory of this German physicist. They waited. The moon covered the sun. The sky went dark. They photographed the stars. They developed the plates. They measured the positions. And Einstein was right. The starlight was bent by the exact amount his equations predicted. In that moment, Newton's clockwork universe was officially dead. We lived conclusively in Einstein's universe, a universe that was alive, pliable, and curved. And with that one discovery, the floodgates opened. If light bends, that means gravity can act as a gravitational lens. A massive galaxy cluster can magnify the light of a galaxy hidden behind it, creating beautiful, distorted arcs and Einstein rings. We use this cosmic telescope today to see the oldest, most distant objects in the universe. If time is part of the fabric, then time must also bend. Clocks in stronger gravity, deeper in the dent, must tick slower than clocks that are higher up. This is gravitational time dilation, and it is proven. A clock at sea level runs measurably slower than a clock on a mountaintop. Your head, being slightly farther from the center of the Earth, is aging faster than your feet. This is the very correction our GPS satellites must make every single day, to account for the fact that their clocks, in weaker gravity, are ticking faster than ours on the ground. And finally, there was one last prediction. A prediction so strange, Einstein himself was unsure of it. If spacetime is a fabric, what happens when you disturb it? What happens if two of the most massive objects in the universe, two black holes, spiral into each other and collide? The equations said they should shake the fabric. They should send out ripples of pure gravitational energy, propagating outward at the speed of light. Gravitational waves. They would be, Einstein calculated, impossibly small. By the time they reached Earth from a distant collision, they would stretch and squeeze our entire planet by a distance smaller than the width of a single atomic nucleus. He was convinced we would never find them. But we built a machine of impossible sensitivity. The Laser Interferometer Gravitational Wave Observatory, or LIGO. And on September 14, 2015, almost exactly 100 years after Einstein predicted them, the alarm bells rang. A signal had arrived. It was a chirp that lasted less than a second. It was the sound. It was the sound of two black holes, a billion light-years away, merging into one. It was the sound of space-time itself, ringing like a bell from the most violent event in the cosmos since the Big Bang. It was the final, triumphant confirmation. We do not live in a clockwork. We live in a cosmos that is dynamic. A universe that stretches, that shrinks, that bends, and that sings. These ideas, they are more than just facts. They have a way of seeping into your consciousness, of changing the way you see the sky, the way you feel the floor beneath your feet, the way you experience the passage of your own life. If you feel that shift, that sense of wonder, or even a quiet sense of peace in the face of this vast, strange, and beautiful reality, that is the heart of this journey. And if you would like to be here for the next chapter, as we explore the origin of this fabric itself, I invite you to subscribe, and perhaps even to click that small, quiet bell. It ensures you will be notified when the next part of this story is ready to be told, and it lets the wider world know that these deep, quiet thoughts still matter. We have spoken of space-time as a fabric, a substance that can be bent, twisted, and torn by the things that live within it. We have seen how stars and black holes can dent this fabric, creating the divots we call gravity. We have explored the hypothetical tunnels, the wormholes, that might, in theory, bridge it. But all of this, all of our discussion, has been local. It has been about the parts of the universe. Now, we must ask the largest question of all. What about the fabric itself? What is the story of the whole infinite tapestry? Where did space-time, as a single object, come from? To answer this, we must go back to the darkness. For all of human history, we have looked up at the night sky and seen a profound, deep, and comforting blackness, punctuated by the diamond dust of stars. And in that blackness, we have also found a paradox. A simple question, first asked in the 1800s, that tears the old universe apart. Why is the night sky dark? This is Olbers's paradox, and it is a devastatingly simple piece of logic. In the old Newtonian universe, the one that existed before Einstein, the cosmos was assumed to be infinite in size, infinite in age, and static. It was just there, forever. But if that is true, then in any direction you look, your line of sight must eventually end on the surface of a star. If you look through a forest, you see the dark spaces between the nearby trees. But if the forest is infinite, those gaps will be filled by the trunks of trees farther away and farther still, until the entire view is just a solid wall of tree. So it should be with the stars. If the universe is infinite and eternal, every single point in the night sky should be as bright as the surface of the sun. The entire heavens should be a uniform, blazing, white-hot inferno. But it is not. It is dark. This darkness is the first clue. It is the universe screaming to us that one of our assumptions is wrong. And in the 1920s, an American astronomer named Edwin Hubble, using the most powerful telescope of his day, discovered which one it was. He was not just looking at fuzzy nebulae within our own Milky Way, as many thought. He was proving that these smudges of light were, in fact, island universes. Other galaxies, just like our own, but millions of light-years away. And then he found the second clue. He was measuring the light from these distant galaxies, and he found that it was wrong. It was stretched. The specific known frequencies of light from elements like hydrogen were not where they should be. They were all shifted toward the red end of the spectrum. This is a redshift. He understood this to be a Doppler effect, the same effect that makes a passing ambulance's siren drop in pitch. If the siren is moving away from you, the sound waves are stretched, and the pitch sounds lower. Hubble concluded that the red shift meant the galaxies were all moving away from us. And not just that. He found a stunning correlation. The farther away a galaxy was, the faster it was moving away. This was a revelation that seemed to place humanity, once again, at the absolute center of existence. Everything in the cosmos was fleeing from us. But Einstein's new theory of gravity, general relativity, offered a different and far more profound interpretation. The galaxies are not moving. The light is not redshifted, because the galaxies are flying through space away from us, like cosmic debris from an explosion. No, the light is redshifted because the space between the galaxies is expanding. The fabric itself is stretching. A photon of light traveling for 1 billion years, is riding on this expanding fabric. And, as the fabric stretches, the light wave itself gets stretched along with it. Its wavelength gets longer and it becomes redder. This is the cosmological redshift. And it means there is no center. Imagine a balloon with tiny dots painted on its surface. You begin to inflate it. If you are an ant standing on any dot, you will look around and see all the other dots moving away from you. And the dots that are farthest away will, because there is more balloon to stretch between you and them, appear to move away the fastest. There is no center of the expansion on the surface of the balloon. The center is in a higher dimension, in the very act of inflation. We are all on that balloon. Every galaxy. The universe is expanding, everywhere, at once. This was it. This was the answer to Olbers's paradox. The night sky is dark because the universe is not static. The light from the most distant galaxies is redshifted, stretched so much by the expanding space that it has been moved out of the visible spectrum, into the realm of invisible microwaves and radio waves. And, crucially, the universe is not infinitely old. There was a beginning. We can only see light from stars that has had time to reach us. And this is the ultimate implication. If the universe is expanding, what happens if we run the film backward? If we reverse this great cosmic inflation, all the galaxies, all the dots on the balloon would rush back towards each other. The space between them would shrink. The entire observable universe, all of its 100 billion galaxies, would get smaller, and smaller, and smaller. The fabric of space-time would compress, and as it compressed, it would get hotter, and denser, until, logically, you must arrive at a moment in the finite past, a moment somewhere around 13.8 billion years ago, a moment when all the space, all the time, all the matter and energy in the entire universe was compressed into a single infinitesimal point of infinite density, infinite temperature, and infinite curvature. This moment is the Big Bang. This is the most misunderstood name in all of science. The Big Bang was not an explosion in space. It was not a bomb that went off in a pre-existing empty void. It was the explosion of space. It was the beginning of the fabric itself. It was the birth of space, and the birth of time, and the birth of all the laws that govern them. Before it, there was no before. Asking what happened before the Big Bang is, in the framework of relativity, a meaningless question. Time itself began at that instant. There was no Thursday before the first Friday. It is, as Stephen Hawking so perfectly put it, like asking, what is north of the North Pole? It is a concept that simply does not apply. At that first instant, the universe was not a place. It was a quantum foam, a singularity, a state that our current physics, our beautiful theories of relativity and quantum mechanics cannot describe. They break. They give us answers of infinity, which is just math's way of saying, I do not know. But in the tiniest, first fractions of a second after that moment, physics as we know it began to congeal. The universe, an expanding fireball of pure energy, began to cool. The fundamental forces split off from one another. And for the first 380,000 years, the cosmos was a blazing, opaque fog of superheated plasma, a place where light itself was trapped, constantly bouncing off a sea of free-roaming electrons. And then the universe cooled enough. It dropped below a few thousand degrees, and the universe, became transparent. The electrons were finally captured by protons and neutrons, forming the first stable atoms. The light, which had been trapped in the fog, was now suddenly set free. A great, blinding flash of light, released from every point in the cosmos at once, began to travel outward, forever, into the newly formed, expanding darkness. That light is still traveling. It is still here. In the 1960s, two radio astronomers, Penzias and Wilson, were trying to use a large radio antenna and were bothered by a persistent, faint background hiss. It came from everywhere in the sky, day and night. They cleaned the antenna. They shielded it. They even removed some nesting pigeons. The hiss remained. What they had found, by accident, was the single greatest discovery in cosmology. They were hearing the afterglow of the Big Bang. That flash of light, released 380,000 years after the beginning of time, has been traveling for 13.8 billion years, and in that time, the universe has expanded so much that this brilliant, white-hot light has been stretched, all the way down, past red light, past infrared, into the cold, faint hiss of the microwave spectrum. It is called the cosmic microwave background radiation. You are, right now, at this very second, being bathed in it. A small percentage of the static on an old, untuned analog television is the sound of the creation of the universe. We have photographed it. The maps of the CMB are baby pictures of the cosmos. They show a universe of almost perfect, almost uniform temperature. And this, perfection, led to two more enormous problems. The flatness problem. Why is the universe flat? We know that mass curves spacetime. The total stuff in the universe, its density, determine its shape. If there is too much stuff, gravity wins and the universe is closed, like the surface of a sphere. It would eventually collapse back on itself in a big crunch. If there is too little stuff, the universe is open, like the surface of a saddle. It would expand forever. If the density is exactly right, in perfect knife-edge balance, the universe is flat. Parallel lines stay parallel forever, and our measurements of the CMB show us that our universe is astonishingly flat. It is balanced to a precision of 1 part in 10 to the power of 60. This is like finding a pencil balanced perfectly on its sharpest point, and it has remained that way for 13.8 billion years. It is too perfect. It cannot be an accident. The horizon problem. Why is the CMB so uniform? When we look at the CMB map, the temperature of the sky in one direction and the temperature of the sky in the exact opposite direction are identical. But in the 13.8 billion years since the universe began, these two regions, which are now 28 billion light-years apart, have never been in causal contact. They are too far apart for light, or heat, or any information to have ever traveled between them. So how do they know to be the same temperature? How did they coordinate? This was a disaster. The Big Bang theory, as beautiful as it was incomplete. It was broken. We needed a new idea. And in the 1980s, a physicist named Alan Guth provided it. He called it inflation. He proposed that the Big Bang was not a simple, steady expansion. He proposed that in the first, tiniest, inconceivable fraction of a second, a time so small it makes a nanosecond look like an eternity, the universe underwent a period of hyperexpansion. It did not just expand. It inflated exponentially. In a flash, it doubled and doubled and doubled again, growing from a size smaller than a proton to the size of a marble, faster than the speed of light. This doesn't violate relativity, by the way. Objects cannot move through space faster than light. But space itself, space can do whatever it wants. This one wild idea solved everything. It solves the flatness problem. Imagine a tiny, wrinkled, curved balloon. If you inflate it to the size of the entire Earth, your patch of it, the part you can see, will appear perfectly, mathematically flat. Inflation flattens the universe by expanding it to an incomprehensible scale. It solves the horizon problem. Before that flash of inflation, those two opposite sides of the sky were in contact. They were neighbors, huddled together in that first infinitesimal speck. They did have time to share their temperature, and then, in an instant, they were ripped apart, thrown to opposite ends of the observable cosmos, carrying that thermal memory with them. It even solved a third problem. Where did structure come from? In that first quantum speck, tiny, random quantum fluctuations would have been bubbling. Inflation would have frozen those fluctuations and stretched them to cosmic size. These tiny quantum-scale ripples, stretched across billions of light-years, became the seeds for everything. The slightly denser patches became the spots where gravity would, over billions of years, pull matter together to form the first stars, the first galaxies, and, eventually, us. We are, in the most literal sense, the children of a quantum fluctuation, amplified by cosmic inflation. And so, the story seemed complete. We had a beginning, we had a mechanism, and we had a simple, lingering question that would define the next era of cosmology. What is the end? For decades, this was the great cosmic battle. Is there enough stuff, enough matter, enough galaxies, enough gravity to stop this expansion? Will gravity one day win and pull everything back together in a fiery big crunch? Or is there not enough? Will the expansion just coast, slowing down but never quite stopping, with the universe expanding forever into a cold, dark, empty big freeze? In 1998, two teams of astronomers set out to answer this once and for all. They used distant supernovae, dying stars that act as standard candles, all exploding with the same known brightness, to measure the expansion rate of the universe very precisely. They were not looking for if the expansion was slowing down. They were measuring how much it was slowing down. They took their data, they ran the calculations, and they found the single most terrifying, unexpected, and revolutionary discovery of our time. The expansion is not slowing down, it is speeding up. In the last 6 billion years or so, the universe has stepped on the gas. Something new has taken control. This was not a small error. This was a cosmic revolution. It meant that our fate was not the big crunch. It was not a gentle coasting big freeze. It was something else. To explain this anti-gravity, this force that is pushing the fabric of space-time apart, faster and faster, we had to admit our total, profound ignorance. We had to give it a name: dark energy. It is not matter. It is not a particle. It seems to be the energy of empty space itself, a property of the fabric. Einstein had actually predicted it, in a way. He called it a cosmological constant, and then called it his biggest blunder. He may have been right all along. So, here is the cosmic inventory. Here is what your universe is actually made of, according to our best modern measurements. If you take all the stars, all the planets, all the gas, all the black holes, all the laptops, and all the people, all the normal matter that we can see and touch. It adds up to 5%. About 27% is something else, an invisible, unknown substance we call dark matter. We know it is there. We can see its gravity. It is the invisible scaffolding that holds galaxies together. Without it, they would spin themselves apart. But it does not interact with light. We cannot see it. We have no idea what it is. And the rest? The vast, dominant majority? 68% of the entire universe is dark energy. This is our reality. 95% of the cosmos is made of two substances, dark matter and dark energy, whose names are just polite scientific terms for we have absolutely no idea. This dark energy is now the master of the cosmos, and its acceleration is sealing our fate. It means the future is not just a big freeze, it is a big rip, or perhaps more accurately, a big lonely. As space itself expands, faster and faster, it will begin to pull things apart. First, the great clusters of galaxies will be torn from each other. Then, the galaxies themselves will be pushed apart, faster than the speed of light. In 100 billion years, an observer in our own dying Milky Way will look up, and they will see nothing. Every other galaxy will have been pushed over the horizon, their light red-shifted into oblivion, their presence erased from the sky. The sky will be black, empty. Those future observers, if any exist, will be trapped in a tiny, local island universe. They will look up at their dark sky, and with no evidence of expansion, no redshift, no cosmic microwave background, they will conclude that the universe is static, eternal, just as we did. They will never know the truth. They will never know there was a Big Bang. They will never know that the cosmos was once filled with 1 trillion other islands of light. We, it turns out, are living in a precious, fleeting, cosmic afternoon. We are alive at the one time in the universe's long history when we can still see the evidence. We can still see our own origin, written in the faint microwave echo of the beginning, and in the distant, red-shifted light of our departing neighbors. The darkness we see between the stars. It is not just an absence, it is the future, and it is coming for us all. We have sailed the cosmos on a ship of pure thought. We have ridden Einstein's gentle curving waves of space-time, and we have plunged into the one-way, time-bending traps of his black holes. We have even watched the entire tapestry of the universe, the fabric itself, be born in a flash and expand for billions of years, driven now by a dark, invisible energy. In all of this, in this grand cosmic story, the fabric has been our foundation. Space-time has been the stage. But what if the stage itself is an illusion? What if this smooth, beautiful, predictable geometry that Einstein gave us is just a large-scale approximation? A high-level, simplified map of a territory that is, at its true foundation, nothing like the map at all? What happens when we take our journey and we zoom in? We zoom past the galaxies, past the stars, past the chair you are sitting on, the skin on your hand, the cells, the atoms. We zoom past the electron, a fuzzy cloud of probability. We push past the nucleus into the realm of the quarks. We keep going, smaller and smaller, until we arrive at the absolute bedrock bottom of reality. The place where the rules themselves are born. Here, in this sub-microscopic world, Einstein's beautiful, smooth-sailing ship crashes. It crashes into a reality that is violent, chaotic, and fundamentally terrifyingly uncertain. Welcome to the quantum realm. This is not a place, it is a set of rules, and it is the single greatest intellectual chasm in all of human history. For a century, we have lived with two perfect, beautiful, and utterly contradictory theories of the universe. In one corner, we have general relativity, Einstein's masterpiece. It is the physics of the large, of planets, stars, galaxies, and the cosmos. It is a world of smooth curves, of cause and effect, of perfect prediction. It says that if you know the position and momentum of a planet, you can know exactly where it will be in 1,000 years. It is a universe of deterministic grace. In the other corner, we have quantum mechanics, the physics of the small, of atoms, electrons, photons, and the subatomic zoo. It is a world of probabilities, of maybes, of fundamental uncertainty. Quantum mechanics says you can never know exactly where an electron is and where it is going. The very question is meaningless. The electron, when you are not looking at it, is not a thing. It is not a tiny dot in a specific place. It is a wave of probability, a smear of potential. It is everywhere it could possibly be, all at once. It is only when you, the observer, look, only when you perform a measurement, that this wave of maybe suddenly collapses into a single is. The electron appears at a single point, as if it has made a choice, just for you. This is the famous, and perpetually baffling, double-slit experiment. Fire a beam of electrons at a wall with two tiny slits, and the electrons will, as if they know you are not watching, pass through both slits at the same time. They will then interfere with themselves on the other side, creating a wave pattern. But the instant you place a detector at one slit, to peek and see which way the electron really went, the entire game changes. The electron, as if annoyed, picks a side. It behaves like a simple, stupid bullet. It goes through only one slit, and the beautiful wave pattern vanishes, replaced by two simple, boring lines. The universe, at its core, does not like to be observed. The very act of measuring reality changes what that reality is. Now, take these two theories. Relativity, a smooth, predictable fabric of spacetime. Quantum mechanics, a chaotic, probabilistic world of maybes that collapses when observed. And try to put them together. Try to ask a simple question. What does gravity do to an electron? The entire system breaks. The math gives you answers that are infinity. And infinity is not a number. It is the sound of two gods shouting at each other in a language we cannot understand. This is the war. The physics of the large and the physics of the small are two perfect descriptions of a universe that cannot, according to their own rules, be the same universe. So, let's go looking for the battlefield. Where do these two theories collide? They collide at the Big Bang. They collide at the singularity inside a black hole. And they collide, right now, everywhere, in the vacuum of empty space. We have, for this entire journey, been talking about empty space. But now we must be precise. There is no such thing. The vacuum, according to quantum mechanics, is the single busiest place in the cosmos. Because of the Heisenberg uncertainty principle, which is the fundamental law of maybe, the universe cannot be perfectly certain that a patch of space is empty. Energy and time are linked in this uncertainty. It means that for very, very tiny fractions of a second, the vacuum can borrow a little bit of energy from nowhere, from the bank of reality itself. And what did Einstein teach us? E = mc2. Energy is mass. So, for an infinitesimal moment, this borrowed energy can burst into existence as a pair of particles, a particle of matter and a particle of antimatter. These are the virtual particles. A pair, an electron and a positron, a quark and an antiquark, flashes into existence. They see each other, and in a fraction of a femtosecond, they annihilate, crashing back together and vanishing, repaying the energy loan so quickly the universe barely notices. This is not a theory. This is not a nice idea. This is quantum foam. It is the texture of reality. The empty space between you and this sound is, right now, a roaring, seething, chaotic ocean of particles being born and particles dying, a constant storm of creation and annihilation. We have measured this. We have proven it. The Casimir effect, which we spoke of before, is the measurable push of this quantum storm. It is real. Okay, so the vacuum is not empty. It is full of this foam. It is a sea of fleeting energy. Now, what does Einstein's theory say? Einstein's theory says that energy has gravity. Energy curves spacetime. So, if the vacuum is full of this quantum energy, it must have gravity. It must have a weight. This is the moment where the entire story of physics should have ended. This is the vacuum catastrophe. When physicists first sat down and tried to calculate how much energy this quantum foam should have, they got a number. And when they took Einstein's equations and they tried to calculate how much gravity this energy should produce, they got a number. And this number was not just wrong. It was the single most incorrect, most baffling, most horrifyingly wrong calculation in the history of human thought. The theory predicted that the energy of the vacuum should be 1, followed by 120 zeros, times stronger than all the matter in the cosmos. If this calculation were true, if this quantum gravity of the vacuum was real, the universe would have torn itself to shreds. The fabric of space-time would have been ripped apart, with such explosive, repulsive force that a single atom could not have formed. The Big Bang would not have even lasted a single yoctosecond. But we are here. We are living in a universe that is calm, stable. We are not being ripped apart by the vacuum. This means that somehow all of that unimaginable, roaring quantum energy has no gravitational effect, or almost none. That dark energy we spoke of, the force that is accelerating the universe's expansion, it is there, and its measured value is tiny. It is a 1, with 120 zeros after the decimal point. This is the great, unsolved mystery. Why is the universe so stable? Why is the vacuum so light? Somehow, the universe knows to cancel out all of that quantum energy, to a precision of 120 decimal places, leaving just a tiny, tiny leftover, which we now call dark energy. It is a number so precise, it is like finding a bomb that could destroy a galaxy, but has been dudded by a single, perfect counterbalancing force. We have no idea why. So, we must go deeper. We must zoom in, past this foam, to a place where the rules themselves might finally make sense. We must go to the Planck scale. This is the bottom floor of reality. The Planck length is about 10 to the minus 35 meters. It is a number so small, it is meaningless. It is a distance so tiny that if you were to scale an atom up to the size of the entire observable universe, the Planck length would be the size of a single tree. This is not just a small number. This is the resolution of the universe. This is the pixel. At this scale, the very idea of space and time breaks down. At the Planck scale, spacetime is no longer a smooth fabric. It is not a foam. It is a state of pure chaotic information. The words here and there no longer apply. The concept of before and after dissolves. This is the true battlefield. This is the realm of quantum gravity. We need a new theory, a theory of everything, a single set of equations that can describe the pixel and the cosmos. We do not have it, but we have candidates. The most famous and most ambitious is string theory. String theory proposes a breathtakingly beautiful and utterly untestable idea. It says, if you zoom in on any particle, an electron, a quark, a photon, you will find it is not a point at all. It is a string, a tiny, one-dimensional, vibrating loop of pure energy. And everything is made of these strings. In this picture, the universe is not made of matter. It is a symphony. The way a string vibrates determines the note it plays. Vibrated in one way, and it looks and acts like an electron. Vibrated another way, it looks like a photon. Vibrated in a different way, and it looks like a graviton, the quantum particle of gravity itself. In one single, elegant idea, all of reality, all the forces, all the matter, is unified. It is all just the music being played by these fundamental strings. It is, perhaps, the most beautiful idea in the history of science. But to make the math work, to make the symphony sound right, it comes with a cost, a profound cost. The theory demands that the universe does not have 3 dimensions of space and 1 of time. String theory only works if the universe has 10 or 11 dimensions. So where are they? Where is this vast, extra hidden reality? The theory suggests they are curled up. They are compactified, so impossibly small that we cannot see them. Imagine a power line, a high wire, stretched across a canyon. From a mile away, it looks like a simple, one-dimensional line. But for an ant, walking on that wire, it is not a line. It is a rich, complex, 3-dimensional world. The ant can walk forward and back, but it can also walk around the circumference of the wire. We, in this analogy, are not the ant. We are the distant observer. We only see the big dimensions: length, width, height, and time. But every single point in the space around you, every pixel, is, according to string theory, a tiny, curled-up geometric shape of 6 or 7 extra hidden dimensions. These tiny, invisible, curled-up dimensions are, in essence, the DNA of the cosmos. The shape of these tiny, hidden geometries is what determines how the strings can vibrate. It is their shape that dictates the laws of physics. If they were curled up in a different way, the electron would have a different charge. Gravity would be a different strength. We would not exist. This is the frontier, a world of pure mathematics, of hidden dimensions, of vibrating strings, of a quantum foam that weighs nothing when it should weigh everything. We are standing at the edge of a chasm, shouting our best guesses into the dark, and hoping to one day hear an echo. We are all, in this moment, observers. Each of us in our own local frame of reference, in our own patch of space-time, looking at the same shared and impossible mystery. It makes you wonder. As my voice reaches you, as you create your own now by the act of listening, where are you? What time is it in your part of the world? Are you in a place where the sky is dark and the stars are out? Or is the sun shining, bathing you in the light of our own local nuclear furnace? It is a strange and comforting thought, isn't it, that no matter the answer, the same impossible, beautiful rules. Apply. We have come to the end of the map. We have traveled from the illusion of time to the engines of gravity, from the birth of the cosmos in a flash of inflation, to the strange quantum rules that govern the impossibly small. We have, in essence, explored the two great pillars of our reality: Einstein's relativity, the law of the large, and quantum mechanics, the law of the small. And we have found them at war. We have found a universe that, at its seams, does not make sense. A cosmos built on two sets of laws that are fundamentally, beautifully incompatible. And so we arrive at the final question, the one that lies waiting at the bottom of all the others. What if we have been wrong this entire time? What if the fabric of space-time, the stage we have been talking about, is not the cause of everything but the consequence of something else? We have, for this entire journey, assumed that space-time is the floor. It is the fundamental reality. It is the thing that bends, and twists, and expands. But what if space-time is not the floor? What if it is just a pattern, an illusion, a collective phenomenon, like the temperature of a room? Think of this. A single atom, a single molecule of air, does not have a temperature. The very concept of temperature is meaningless for one atom. Temperature is an emergent property. It is the average motion, the collective, statistical behavior of trillions of atoms, all moving and bouncing together. The thing we call temperature is not fundamental. It is a high-level, human-friendly description of a much more complex, underlying quantum reality. What if space-time is the same? What if distance, length, width, height, and even time are not fundamental properties of the universe? What if they are just the temperature of the cosmos? What if they are the emergent, large-scale, average behavior of something far deeper, stranger, and more quantum mechanical? This is the great frontier of modern physics. The idea that space-time is not fundamental, but that it emerges. And if it does emerge, what does it emerge from? What are the atoms of space-time? The most profound, most magical, and most spooky candidate is a concept that Einstein himself famously hated: quantum entanglement. We have spoken of it before. It is the spooky action at a distance. It is the phenomenon where two particles, born together or interacting in a certain way, become linked. They are no longer two separate things. They are two parts of a single, unified quantum state. You can separate them. You can put one in a lab in Tokyo and the other in a lab in New York. You can send one to the Andromeda Galaxy, 2.5 million light-years away. And the instant you measure the particle in Tokyo, the instant you ask it, "What is your spin? Are you up or down?" it gives you an answer. Let's say it answers up. In that exact same instant, faster than light, faster than anything. The particle in the Andromeda Galaxy, a particle you have not touched or seen, its state is now also known. It is down. It did not become down. It did not receive a signal. They were never two particles. They were one, smeared out maybe, that just happened to exist in two places at once. When you forced one part to be something, the other part instantly became its opposite. This non-local connection, this spookiness, is the true foundation of the quantum world. And now, physicists are proposing the most radical idea since Einstein. What if this is what space-time is? What if the distance between 2 points is just a measurement of the amount of entanglement between them? What if the universe is not a place where entangled particles live, but rather the universe is the web of entanglement? In this mind-bending picture, two atoms that are highly entangled are, in this deeper reality, close to each other. Two atoms that are not entangled are far apart. The geometry of our universe, the very space you feel around you, might just be a map of the total quantum entanglement of all its parts. What, then, is a wormhole? That tunnel through space-time we dreamed of? Perhaps it is not a tunnel at all. Perhaps it is just a massive entanglement, a spooky, non-local thread that connects two regions of space-time that are, in the normal way, very far apart, and thus unentangled. In this view, the fabric of reality is not woven from space-time. It is woven from these invisible, instantaneous quantum connections. And space-time is just the pattern that emerges from the weave. This idea that the deep structure of the universe is built from quantum connections is what finally solves the greatest puzzle of all, the one we found at the edge of the black hole. Let us return one last time to that paradox, the black hole information paradox. The problem, you will recall, was a war. Einstein's relativity said the black hole must have a smooth, harmless event horizon. Quantum mechanics said the information that falls in must be preserved. But the most important clue was the one we almost skipped. The Bekenstein-Hawking formula. The discovery that the information content, the entropy, of a black hole was not proportional to its three-dimensional volume. It was proportional to its two-dimensional surface area. This was the clue. This was the Rosetta Stone of quantum gravity. It was as if you found a library, and you discovered that the total number of books it could hold depended not on the size of the library, but on the paint on its walls. It meant that all the information about everything that had ever fallen into that three-dimensional hole, every star, every planet, every person, all of that three-dimensional stuff could be and must be perfectly and completely encoded on the flat, two-dimensional surface of its event horizon. It was as if the 3D stuff was just a projection, and the 2D surface was the source code. In the 1990s, physicists like Gerard 't Hooft and Leonard Susskind took this one crazy idea, and they applied it not just to black holes, but to us, to everything. What if the black hole is not an exception? What if it is the rule? This is the holographic principle. It is the single most bizarre, most counterintuitive, and most powerful idea in modern physics. It is the conjecture that this vast three-dimensional universe you are in, the feeling of depth in the room around you, your ability to move forward, up, and left, is an illusion. It is a hologram. The theory proposes that our entire three-dimensional cosmos is nothing more than a projection of information that is stored on a vast, distant, two-dimensional boundary, a cosmic screen at the edge of observable reality. You feel solid. You feel like you have volume. You feel like you are moving through space. But in this picture, all of this, your body, this planet, the most distant galaxy, is a three-dimensional image projected from a two-dimensional film. Just as a hologram on your credit card, which is a flat, 2D surface, can store all the information needed to project a seemingly 3D image. Our 2D cosmic boundary contains all the bits of information, all the code, needed to project the seemingly 3D universe that we experience. This is the answer. This is the peace treaty in the war, because it solves the conflict. It says the source code, the 2D film at the boundary. That is the realm of quantum mechanics. It is a flat world of bits and information and uncertainty, with no gravity at all. And the projection, the 3D hologram that we live in, that is the realm of Einstein's relativity. The gravity that we feel, the curvature of spacetime, is not a fundamental force. It is not real in the way we thought. Gravity, in this picture, is an emergent illusion. It is a thermodynamic effect. It is the statistical average of all those quantum bits on the distant 2D screen. It is a hologram of a deeper, flatter quantum reality. If this is true, then reality, at its very bedrock, is not made of matter or energy or space-time. Reality is made of information. And this leads us to one final door. A final, dark, philosophical hallway at the end of physics. If the universe is, at its root, just information. If the laws of physics are just the rules for processing that information, if space-time is just the emergent structure of that computation, if gravity is just a holographic projection, if the universe is, in essence, a giant computer, are we living inside a simulation? This is no longer just a late-night thought experiment. It is a genuine, logical, and unsettling question. The argument is one of statistics. It states, any civilization in any universe that becomes advanced enough to create a perfect, conscious, simulated reality will almost certainly do so. They might do it for research. They might do it to study their own past. They might do it for entertainment. And they would not just run one simulation. They would run thousands, millions, billions. Soon, the number of simulated realities, with simulated conscious beings living inside them, would vastly, infinitely outnumber the one single base reality. So, here we are. What are the odds that we, of all the conscious minds that have ever existed, just happen to be in the one, true, base reality? The odds, statistically, are not just low. They are zero. It is, by this logic, almost a certainty that we are living inside one of the simulations. That the Big Bang was just the moment the computer was booted up. That the laws of physics are just lines of code. That the speed of light is the processor speed of the cosmic computer. The ultimate speed limit for how fast the simulation can render information. That the Planck length, the pixel of reality we found, is literally that. The fundamental resolution of the simulation. The smallest bit, beyond which the program does not bother to render. And what about quantum mechanics? That bizarre rule that a particle is just a wave of maybe until a conscious observer decides to look at it? Well, if you were a programmer writing a simulation for an entire universe, you would not waste the processing power. Why render the exact position of every single atom in the cosmos all the time? You would not. You would program a shortcut. You would write the code so that the atoms, the electrons, remain in a state of maybe until a player, a conscious mind inside the game, decides to look at it. Only then would the program bother to render the result. The observer effect is not a mystery. It's just efficient coding. So, what are we? Are we a dream of a black hole? A hologram projected from the edge of time? A piece of code running on a machine so vast it is indistinguishable from a god? The truth is, we do not know, and we may never know. We have traveled from the river of time to the death of stars, from the birth of the cosmos to the pixels of reality. And at the end of it all, we are not left with a cold, hard answer. We are left with a deeper, richer, and more profound mystery. A mystery that suggests the universe we live in is not just stranger than we imagine. It is stranger than we can imagine. And you are not just a passive observer of this mystery. You are the universe itself. You are a collection of these holographic bits. You are a pattern woven from these spooky quantum threads. You are a piece of the code. You are the cosmos, waking up and asking, what am I? And that, in this world or any other, is the only magic that has ever truly existed. And so, we stand at the end of all our maps. We have arrived at a place where our most trusted guides, Einstein and Bohr, have led us to a cliff edge, pointed into a fog of infinities, and shrugged. We have deconstructed the universe, only to find that the pieces do not seem to fit. We have found that the solid, dependable, three-dimensional world we touch and see and live in is, perhaps, a phantom, a projection of information, a hologram. We have found that the unstoppable, one-way river of time may be a stubborn illusion of our own minds, and that all of reality, your birth, this moment, your death, is a single, frozen, four-dimensional sculpture. We have found that the empty space between us is a roaring, chaotic foam of virtual particles, a sea of energy so vast it should have annihilated the cosmos before it even began. And yet, for a reason we cannot name, it does not. We have found that the laws of this place, the quantum rules, seem to imply that reality is nothing but a smear of maybe, until a conscious mind decides to look and forces the universe to pick a side. We have found that we may be living in a simulation, and here, in this quiet, dark, and final place, we must face the great and perhaps a terrible so what? What does this mean? If the world is a hologram, is your joy less real? If time is an illusion, is your grief meaningless? If we are living in a simulation, does love just not count? This is the great human fear, that in finding the code of the universe, we will find that it is cold, mechanical, and that we, with our passions, our art, our fears, and our dreams, are just a glitch in the program, a rounding error, a biological accident on a damp rock, inside a holographic projection running on a computer we cannot even imagine. This is the abyss, the existential dread that comes at the end of physics. But what if we are wrong? What if, in our fear of being meaningless, we have missed the entire point? Let us, for this final part of our journey, not look out, but look in. Let us dare to propose a different answer. What if we are not the glitch? What if we are the point? This is the participatory universe, an idea born from the same quantum weirdness that gives us the observer effect. It is an idea that flips the entire story on its head. It suggests that the universe does not and cannot exist in a real state without us. It suggests that consciousness, our awareness, is not a side effect of the cosmos. It suggests that consciousness is the co-creator of it. Think of it. The quantum rules state that a particle is just a wave of probability, until an observation collapses it into a single real particle. Well, what observes the universe? What, or who, collapses the wave function of the entire cosmos. The participatory model suggests that the universe exists as a vast, shimmering quantum maybe, a superposition of all possible histories, all possible realities, all at once, until a form of consciousness evolves within it. A part of the maybe wakes up. A part of the code becomes self-aware. And in that moment, by the very act of observing, that consciousness reaches back through all of time, all 13.8 billion years, and it collapses the wave function of its own past. It is the act of you, looking at the stars, that forces the stars to have been there in that specific way to create the light that is now entering your eye. In this beautiful and terrifying picture, the universe is not a simulation we are trapped in. It is a story that we are collectively telling to ourselves. You are not an accident. You are a necessity. You are the universe's way of making itself real. So let us go back one last time to all those strange, cold ideas, and let us look at them through this new lens. This lens where you are the focus. What of the block universe? That cold, static, frozen reality. If we are co-creators, then the block universe is not a prison. It is a tapestry. It means that the moments of your life are not fleeting. They are not lost to the past. That moment, years ago, of pure, unadulterated joy, a laugh, a first kiss, the moment you held your child's hand for the first time. That moment is not gone. It is not a memory. It is a permanent, eternal, fixed location in the four-dimensional geometry of space-time. You cannot go back to it, but it will always exist. Its realness is forever, and the moments of pain, of loss, of grief, they are also fixed. They are part of the pattern. They are the shadows that give the tapestry its depth. They are not punishments. They are the curves in the space-time of your life, the gravity that gives your story its shape and its meaning. If the universe is a block, it is not a cold, dead crystal. It is a timeless, finished, perfect work of art, and your life is one of the most intricate, most beautiful threads woven through it. What of the holographic principle? The idea that we are just projections. Well, what is a projection? What is a hologram? A hologram is a miracle of information. It is a way of storing a vast, three-dimensional world on a simple, two-dimensional surface. And its most magical property is this. If you take a holographic plate and you shatter it, every single piece, no matter how small, still contains the entire image. It might be fainter, it might be fuzzier, but the whole is contained in every part. Now, think of yourself. If the universe is a hologram, then you are not just a projection. You are a fragment of the entire cosmic plate. And this means that you, in your small, fragile, biological self, contain the entire thing. The code for the most distant galaxy is also in you. The information of the Big Bang is also in you. The laws that govern a black hole are also in you. You are not a part of the universe. You are a small, holographic, and slightly blurry version of the entire universe. You are, in the most literal way, not just a drop in the ocean. You are the entire ocean in a single drop. This is not New Age philosophy. This is the profound, logical, and breathtaking implication of one of our most advanced physical theories. It does not make you less real. It makes you infinitely more. And finally, What of the simulation? What if this is all, in the end, just a game? Just code? Well, what is the point of a simulation? What is the purpose of a game? A game is not played to get to the end. A game is played for the experience of playing it. If we are in a simulation, then all of the boring parts of the universe, the vast, cold, empty voids, the long, slow, billion-year processes, they are just the back-end code. They are the operating system. But we, with our fragile lives, our 80-year lifespans, our capacity for joy and sorrow and art and music and love, we are the user interface. We are the point of view characters. We are the reason the simulation is being run. The program is not interested in the physics. It is interested in the feeling. It is not interested in the rules of gravity. It is interested in the experience of falling in love. It is a simulation designed to create and to feel and to process meaning. And you are its most advanced, most sensitive, most important player. Your life, your choices, your feelings are not an error in the code. They are the code. They are the data that the entire, vast cosmic computer is trying to generate. Your heart is not an accident. It is the engine of the entire thing. So, here we are. Our journey is over. We began by questioning the simple, steady tick of a clock. We found that time itself is a flexible, personal, and perhaps illusory thing. We fell into the darkness of a black hole and found that reality itself splits in two. A place of frozen time for one, and a one-way trip to the end of time for another. We looked for tunnels and shortcuts in the fabric, and found that they are, in fact, machines for creating paradoxes. We found that the universe might clone itself just to keep its story straight. We journeyed back all the way to the beginning, to a moment before, a singular flash of inflation that flattened the cosmos and planted the seeds of the galaxies, seeds that we are made of. We discovered that this entire beautiful story is being torn apart by a dark, invisible anti-gravity that is accelerating our cosmos into a cold, lonely, and infinite night. We dove down into the pixels of the world, into the foam of the quantum vacuum, and we found a world of maybes and vibrating strings, a world that demands our own consciousness, our own observation to even become real. And finally, we found that this entire three-dimensional stage may be just a hologram, a projection of a deeper, flatter reality made of pure information, and that we are not lost in it. We are, in all the ways that matter, the reason for it. We are the children of the stars. We are the atoms of the cosmos, woken up. We are the universe, observing itself. We are the maybe, become is. We are the threads, and we are the tapestry. And now, our shared now, this moment of connection, comes to a close. It is time to let the observer rest. It is time to let the wave function of your own consciousness dissolve from a definite state into the infinite, unbounded superposition of potential that we call dreams. As you rest, feel the gentle, persistent force of gravity, the dent in spacetime that holds you safely and securely in place. Feel the air, the gift of ancient, exploded stars, fill your lungs, and then release. Let the complex information of the day be archived by your mind. This journey is just one of many. This conversation, it never truly ends. It just pauses. If you would like to be here, when it resumes, if you feel a connection to this shared quest, this quiet, digital place where we gather, the simplest acts are the threads that guide you back. If you feel moved, you can subscribe. Or you can ring that quiet, waiting bell, which ensures you will find your way here again. Or you can simply leave a trace, a thought, a word, a feeling about the one idea that resonated with you in the stillness of your own now. It is a lovely thing to know that in this vast and sometimes lonely cosmos, we are, for a fleeting, holographic, and beautiful moment, observing it together. And now, just breathe. Let your eyes grow heavy. Let the universe cradle you in its quiet, curving, and magnificent arms. Sleep well, and good night.